Welcome back. In this lecture, I will discuss about chain dimensions of polymer molecules, and these are the topics I plan to cover in this particular lecture. Now, we are starting polymer characterization now onwards, and let me give you an overview of polymer characterization. Now, we have studied how to synthesize polymers by different methods, and then we also studied the solution behavior of polymers. Now, we need to understand the nature of the polymers what we have synthesized. For that, we need mainly two types of characterization. One is characterization of physical structure, which means we need to find out the chain dimension, molecular weight of the polymers, and chain shape and skeletal structure or the architecture of the polymer chains. We also need to chemically identify the polymers, what is basically we have synthesized. For that, we need to identify the repeat units and if possible the end groups of the polymer. We need to find out the microstructure in case of homopolymer. For example, if you talk about tacticity, whether we have syndiatactic or isotactic type polymerization, we need to find out the microstructure for homopolymer. For copolymer, we need to find out the chemical composition of the copolymer, what is the weight fraction or mole fraction of the different repeating units in this copolymer, and also what is the nature of the copolymer, whether it is alternating, random or block copolymer. So, basically we need to find out the sequence distribution of different repeat units in the copolymer. If we can do all sort of this characterization, then we can satisfactorily characterize the new polymer. Let us focus on chain dimension, and let us consider the simplest molecule polyethylene, which can be written by this way CH2 and so on. Now, this does not capture the numerous conformations of a polymer chain that can exist. Now, we have discussed conformations before, and just to repeat that these conformations results from rotation around the single bond of the polymer backbone, and as this rotation takes place around the single bond, polymer can exist in different size and shape in a solvent or in a solution. So, basically the size and shape is kind of a dynamic structure of polymers. Polymers structures are not rigid, their shape and size keeps on changing when they are in solution. So, we basically have a average size, we talk about average size or average dimension of polymer molecules in solution. Now, this size and shape depends on the chain length or molecular weight. Obviously, the higher is the molecular weight, higher would be the size of the polymer, given other factors remain same. Chemical structure, if the chain stiffness increases, that means that rotation around the single bond becomes more difficult, then the polymer becomes more stretched or more elongated, and it also depends on the molecular environment, which means polymer and polymer solvent interaction. As you can guess that if the polymer interacts with solvent favorably, then the polymer chain or polymer dimension will expand, because polymer wants to interact more and more solvent molecules. Whereas, if the solvent is not good, it is poor solvent, then the polymer will become smaller in dimension, because it will try to avoid the solvent molecules. Now, we come back and just redefine or revisit these two terms, configuration and conformation. Configuration are the arrangement of atoms through bonds, and different configuration we if we need to interchange between different configuration, then we need to require we actually require bond breaking and making, and different configuration corresponds to different composition of polymers for a common molecular structure, which is possible because of different isomer or different stereochemistries of the repeat unit. On the other hand, conformation means for a given configuration, the possible arrangement of atoms in space, and different conformation does not require any bond breaking or bond making. It basically requires rotation around single bond in the polymer backbone. So, basically these two are example of different conformation which can be obtained by rotating the single bond in the polymer backbone. Now, when you talk about polymer shape, most polymer molecules have relatively flexible background, because most of the polymers we generally talk about are vinylic CH2CC backbone. Even if they are heteroatoms, most of these bonds are single bond, and that is why rotation around this bond is feasible, and as a result the polymer chains tend to be highly coiled. That is why when we write polymer structure, generally we tend to write a coiled structure, not a straight line or a zigzag line. We do not write this way. Most of the polymers have flexible backbone. So, generally when we write polymer, we write as a coiled structure. Now, the conformation of the flexible chain looks like the random flight, which just now I draw is basically we can draw randomly the structure, and this is typical conformation of flexible polymer in solution or melt, and they are called random coil or Gaussian coil. And if the backbone stiffness goes up, which means the rotation around the single bond becomes more and more difficult, the polymer chains actually tend to become more elongated, like ohm like or a rod like structure. So, if you compare, if this rotation becomes difficult, then we have a more longer basically size, and it becomes maybe even a rod like or more elongated structure as the rotation becomes more difficult or the stiffness goes up. Now, when you talk about the size, the first thing we need to know is the contour length, which is nothing but n multiplied by n. N is the number of bonds in the polymer backbone, and L is the length of each bond. So, if I talk about a polyethylene molecule, then if we talk about 10,000 bonds in the backbone, so which is equals to n, then each carbon bond length will have 1.54 Armstrong. So, the contoured length would be 10,000 multiplied by 1.54 Armstrong. So, 15400 Armstrong given by this structure. Next, we need to talk about is the root mean square end to end distance, which is represent as this. Now, as we discussed that we generally write polymer in a coiled dimension, and the distance between two end is called end to end distance. Now, as I explained that this is not a rigid chain structure, there is always rotation around the single bond. As a result, this structure is dynamic, and once in one instant polymer may remain as this, next instant it can remain as this. So, then we have in another end to end distance, or in another instant it can remain like this. In that case, this is my end to end distance. So, which means the polymer chains are not static chains, they are always this different conformation is appearing because of the rotation around single bond. As a result, we consider a average time average dimension. So, that is why this symbol is written. So, this is the average time average quantity. Now, in this case we are talking about end to end distance, which is r in this case. Now, we generally do not write average r, but we write root mean square, because if we write r, then we need to also consider the direction. So, if this is the positive direction, then a direction of this side would be negative direction, then which, so basically averaging will be difficult. Now, if we take a square term, then we need not to consider this sign, then we can make it a square term to remove the sign and then take a square root. This is the standard practice we do when this end to end distance or other chain parameters are considered. So, this is the average time average or mean, root mean square end to end distance. Another parameter we can basically bring into what is called radius of gyration, and this is expressed by this symbol, which is radius of RMS or root mean square distance of the elements of the chains from center of gravity of the coil. If I have a coil structure like this and I have a center of gravity here, and then these are different elements. So, I can draw the distance. So, it is the root means square distance. So, basically if this individual distance are SI, this individual distance are SI, then make a square and then take a average and then take a root of that. So, that will give the radius of gyration, and this is expressed by this is the expression how we express the radius of gyration. And so, in this case SI is the vector distance from center of mass to the ith unit of the chain. Again the square term is done to avoid the sign of the vector. If we need not, we have just, if we had just averaged the absolute value of SI, then sign of the vectors would complicate the matters. To avoid that, it has done by root of the mean of the square term. So, RMS distance it is called. Now, these two are linked mathematically, and for high molecular weight macromolecules that have random coil shape, these two quantities are linked by this expression. Now, the first simplest model for a polymer is freely jointed chain without any restriction. The only restriction is the bond length, for each bond lengths are actually same, which means that we can start from here and we can continue in different direction without any restriction. Only thing we have to maintain the same bond length, which probably I am not doing, but we basically can do any basically way you can. Only thing we need to do, keep the bond length same, which probably I have not done. So, when you draw, you need to keep this bond length fixed. So, this is the freely jointed chain. So, there is no restriction of bond angle or basically there is no steric hindrance between this the bond lengths and so on. And in this case, the size we call is called the RMS end to end distance, and we write a subscript f, which means it is a freely jointed chain, and it is given by this expression n to the power half L. Remember, for without the controlled length we had n into L, and now freely jointed chain, which we have expression n to the power half into L. Obviously, coil dimensions can be significantly lesser than the contour length. So, if you talk about the same example, we have in 10,000 bonds for polyethylene. Now, the value for this end to end distance would be n would be now 10,000 to the power half into 1.54 Armstrong. So, it will be 100 times lower than the contour length for the same molecule, which means the coil dimension for this case significantly lesser than the contour length. Similarly, we have this radius of gyration for freely rotating or freely jointed chain given by this expression. Now, this is useful for theoretical treatment of rubber elasticity, and this term is useful for basically this is directly relevant to the dilute solution properties and light scattering properties. And because we are talking about radius of gyration, it is kind of radius of that coil, and so it is useful in characterizing branched molecule which have more than 2 ends, and cyclic molecules which have basically no loose ends. Now, freely jointed chain, these are very simple model. Real polymer chain have several restrictions. These are the following restriction for that exists for a real polymer chain. One, that it has a bond angle restriction, because we cannot have any angle between two bonds. We also have short range steric restrictions, long range steric restrictions, and excluded volume effect, which we will discuss one by one. Let us talk about bond restriction. See, if we had two bonds, like I have one bond, if I have no restriction of placing the second bond, I can place it here, or I can place it here, or I can place it here. In this case, average, if these all are equally probable, then this would be the average place where bond can be placed. So, in this case, the end to end distance would be, this would be the end to end distance. But actually most of the bond angles are greater than 90 degree. So, actual bond, because of the bond restriction which are fixed, bond angles are fixed. So, which would be actually it would be somewhere here. So, actually the distance between two ends will be more than when it was there was no bond angle restriction. So, bond angle restriction of bond angle greater than 90 actually will increase the average end to end distance. Hence, this was for the no restriction. So, we now add this second term to bring this restriction of the bond angle. So, we write F A as a superscript, which is a freely rotating, there is no restriction about rotation around single bond, but there is a fixed bond angle. The F A stand for angle, bond angle. Okay. Now, usually bond angles are between this 90 degree to 180 degree, which means cos theta is minus 1 to 0, and for a tetrahedral carbon bond length, this is theta is 109.5 degree. Hence, this quantity is 1.4 times than the freely rotating polymer chain. As we discussed that because of the bond angle which is higher than 90 degree, this end to end distance become higher compared to freely rotating chain. So, this is higher than freely rotating chain. Similarly, the radius of gyration would be higher than the radius of gyration of freely rotating chain. Now, next we will talk about the short range steric restrictions, which basically the restriction of dihedral angle. Let us talk about the simple system of N-butane, which structure is we know CH3, CH2, CH2, CH3. Now, we generally represent this simple molecule by two ways. We can represent by Sawhorst projection or Newman projection, and these are the methyl groups. So, when these methyl groups are in opposite direction as shown in these two projections, then we call it say trans, and corresponding dihedral angle is 0, and the C1 to C4 distance is 3.9 Armstrong. Now, if these two CH3 groups in the same direction as shown from this projection, then we call this is cis conformation, and dihedral angle is 180 degree in this particular case, and the C1 to C4 basically the distance between two ends C1 to C4 end to end distance is lower in this case 2.6 Armstrong. But as you can understand, or you can basically anticipate, that if these two methyl groups are in cis position, then there will be steric hindrance among these. So, this conformation is probably less likely than this conformation where these two CH3 groups are opposite to each other. So, the steric hindrance is not there, or steric hindrance is absent. Now, because of this rotation around this single bond, we can have many conformation, and there will be many values of end to end distance between C1 and C4 as we rotate around this single bond, and that is always happening. In case of bond angle restriction is fixed, because bond angles are same for all the time, but in this case because the rotation around single bond always exists, that means we are getting different conformation with time, and as a result the energy of this conformation and the end to end distance will also change. We can plot the potential energy, and from one end to another end, basically we are rotating from one end when the two methyl groups are overlapping with each other, then we rotate 360 degree to starting from minus 180 to plus 180, and when these two methyl groups are farthest apart, dihedral angle is 0, the potential energy is minimum, and there are other Gauss conformation and all these things that you have already studied in your first year chemistry courses. So, as you can see, this cis conformations have highest energy and the trans conformation has lowest energy. So, given a chance, conformation will try to remain here, but because there is freely rotation possible, hence it is not that the conformation will always be like this, but there will be other conformation, but most of the time the molecule will stay in conformation which has lower energy. So, in that case we are adding, for this restriction we are adding this second term. Now, if there is no restriction, then it was between 0 to 180, which means if there is no restriction, the average would have been 90 and cos 90 would have been 0. So, this term would be 1. So, if there was no hindrance, steric hindrance, which we call short range steric hindrance, it would have been 1, but because there are steric hindrance, phi will not be, this is time average. So, phi, the average value of phi will not be 90 degree, but it will be less than 90. So, it will be less than 90 are preferred. So, we will have this term which will be higher than 1. Now, in this case we are writing H A, H is a hindered rotation for H and A for fixed angle, fixed bond angle. Now, this would be obviously higher than when there was no hindrance for rotation around single bond. So, this will be higher than this, as we discussed that the dihedral will be less than 90 degree. Similarly, the radius of gyration would be higher than the freely rotating radius of gyration. When you have, instead of butane molecule, if you have a polymer molecule which have bulky side group like aromatic group in polystyrene, then this becomes more complicated and getting a proper expression for this steric restriction become difficult. So, in that case this all these short range steric restriction are accommodated in this term which is called steric parameter, which is the term which is which basically multiplies this freely rotating chain with fixed bond angle to get the dimension of chain with two restrictions. So, the steric actual value of the steric parameter would be higher than this, as we have bulky side group and this generally varies between 1.5 to 2.5, and so this value where we are writing 0 here or not here, which means this is obtained experimentally, not determined theoretically, and this is approximately 2 to 3 times of the end to end distance, RMS end to end distance for a freely rotating polymer chain, and this dimension we call unperturbed dimension. Next, if we compare the unperturbed dimension and this freely rotating or freely free polymer chain which did not have any restriction of bond angle or dihedral angle, then this ratio gives the stiffness of the polymer chain, which is mentioned as characteristic ratio. So, this value of characteristic ratio indicate how much greater the RMS end to end distance of a real polymer chain compared to that of a freely jointed chain. So, it is the measure of inherent stiffness of a polymer chain. Next, we will go to the long range steric parameter. Now, long range interactions, once a bond occupies a given space in the given volume in a space, no other bond can occupy the same volume. We call this as a excluded volume effect. Basically, if I write a polymer chain like this, then once it occupies that particular space, then the second fragment or second polymer cannot occupy the same place, which actually now we further expand the chain, and this we call excluded volume effect. In case of real polymer chains, this long range interactions, we call this as long range interactions, which causes the chain dimensions to be generally higher than unperturbed dimension, because in unperturbed dimension we did not consider this excluded volume effect. Now, because of excluded volume effect, the polymer fragments need to avoid overlapping with each other, which means the polymer dimension would be even higher. Perturbation of the chain dimension can also happen if there is an interaction between the polymer fragments with solvent molecules. If there is a favorable interaction between the polymer and solvent molecules, then polymer will try to expand further, making the size of the polymer coil even higher. So, in real polymer chain, this we are now removing any subscript, that means we are talking about the real polymer end to end RMS end to end distance, which will be higher than the unperturbed dimension, and this higher we are basically considering this as a expansion factor, which is the ratio of the actual real RMS end to end distance with the RMS end to end distance of the unperturbed dimension, and this is called expansion factor. Similarly, we have expansion factor for radius of gyration. Now, in case of theta solvent, if you can remember that theta solvent means as if the polymer segments are not linked with each other. So, this excluded volume effect does not come, and also there is no interaction, delta H mix is 0. So, there is no contact interaction between the polymer and solvent molecule. So, basically in case of theta solvent, the actual dimension becomes same as the dimension of the unperturbed dimension, which means the expansion value of the expansion factor becomes 1. And if we have a better solvent, good solvent, the expansion factor become more than 1. So, in polymer in dilute solution, generally this expansion factor is more than 1, and in good solvent we have chain expansion, poor solvent we have chain contraction. Theta solvent is exactly the chain contraction exactly compensate the excluded volume effect. We have alpha or expansion factor is equal to 1. So, we have the unperturbed dimension is same as the actual dimension, and this is true for pure amorphous polymer also. In case of polymer amorphous polymer also, the expansion factor for RMS end to end distance and the radius of gyration also 1. So, in summary, in case of chain dimension, if we have good solvent quality, then the polymer solvent will be miscible and we get a soluble polymer, and delta G mixing is negative and the chains are isolated. We are talking about dilute solution. So, chains are well separated from each other and expansion factor is more than 1, and polymer solvent interaction factor is interaction parameter is less than 0.5 or less than half. In case of theta solvent, the polymer is miscible or soluble in the solvent, delta G mix is less than 0 because of the combinatorial entropy as we discussed earlier. Polymer chains are isolated, they are separate from each other, and the expansion factor is 1 and the polymer solvent interaction parameter is equals to half. For a poor solvent, the polymer is just soluble, is basically close to precipitating out, the delta G mixing is less than 0 or almost equals to 0, and the chain starts slowly aggregating. Now, the polymers are already reached the unperturbed dimension. So, it is not possible to further compact the polymer because of the restriction of bond angle and bond rotation. Hence, the expansion factor remains close to 1, but the polymers start basically aggregating with each other, leading to precipitation, and this happens when the polymer solvent interaction parameter value has less than or greater than 0.5. Now, if this goes much higher than 0.5, then the solvent is actually non-solvent, then the polymer is insoluble and delta G mixing is positive and polymers are segregated. But the chain dimension in this case, because they are now they are precipitated out and they are just like pure amorphous polymer, and the expansion factor is close to 1. So, with this I come to end of this lecture on chain dimension, and in the next lecture I will talk about frictional properties of polymer solution.